In the last class, we showed that determinant is equal to this expression 1. Its expression 1 here is this big sum of signed weights of all closed sequences with length exactly equal to n, which is the number of vertices. So this in particular contains cyclic covers, and cyclic covers is another way to look at permutations. So we are actually computing a bigger sum, but then the extra things we showed cancel out. So now what we'll do is we'll show that for some weird reason this big sum is easier to compute than the previous sum. Okay, any questions? Okay, so we'll prove this lemma by Mahajan Vinay. So we'll actually show that there is an ABP of width n square and depth n plus 1. Okay, so there is an n square times n plus 1 ABP where every path from S to T will be implementing a closed sequence with the signed weight exactly as in the expression. So the sum over all the paths will give you determinant. Okay, so before that, let me just point out a physical interpretation of ABP, because that is what we'll be using here. So ABP width you can think of as the number of registers in your machine. Okay, so width corresponds to memory. So registers, and depth corresponds to time. So basically, if you have width many registers, then you can implement any ABP of that much width in time equal to the length or depth of the ABP. So in other words, what we will be doing is we'll show that determinant can be computed using n square registers in time n. Okay, so that is an alternative way to look at this implementation. Now note that width n square or n square registers is not too much, because your matrix already had n square entries. So you can think of the matrix entries being stored one per register, and within those many registers you can actually do computation, and in n time you will have the determinant. Yeah, and when you convert this via matrix multiplication, iterated matrix multiplication into circuit, then you get a different complex, a different interpretation. So there you will get actually log n time. So the things are a bit different there. So this ABP is actually a stronger result, because you can derive the circuit result from here. Right, so the way we will do this is we'll have layers labeled by L varying from n1 to n plus 1. So 1 L equal to 1, L equal to n plus 1 are the source and target vertices, but for L2 to n, layer L2 to n has, each of them have around Each of them has around n square nodes. Which will be labeled by a pair, so I comma j, and the layer label will be in the superscript. For different ij between 1 to n. Okay, so the vertices that you see in a layer are these Vijl. So these around n square, many things you can imagine them to be stored in the registers. Okay, at time L they are stored in the register, and what they represent is well, I will represent the head whose flow we are currently building, or the walk we are doing, and J will be the current vertex. So nothing else will be remembered. Okay, so at time L, all we remember is what is the head of the closed walk that we are currently trying to do, and where are we in the closed walk. Okay, so these two things, and then based on this, you have to take the next step. So that next step will go to L plus 1. Okay, so you will pick an edge. You will pick an edge and you will go to some V I comma j prime superscript L plus 1. So this will be basically in the closed walk. What you are doing is that you are trying to build a flow with the head equal to I, and from jth vertex you are moving to j prime, and the only thing you have to ensure is that both j and j prime are greater than I. Okay, this is the only constraint. So using this nearly oblivious walk, you will be able to complete a flow. So when you come back to I, then the interpretation is that you have completed the walk, closed the walk, and at that point you should introduce a sign. Okay, because every flow introduces a sign of -1, and these -1 then get multiplied out to get the actual sign. Okay, so let us look at the details of the implementation. So the idea is, as I just mentioned, that in Vijl, I remembers, or I in fact is the head, and J the current node. In the current flow being constructed. It is not yet a closed walk, but it is just a walk which will ultimately close back to I. So in particular, I will be less than j. So here actually the subscripts ij denote vertices. They are exactly the vertices. Okay, these are so I has to be smaller than j. Vertices in the graph G. So let me write that down. In fact. And so we intend to hard code a closed sequence as a path. In the ABP. Okay, so this is the overall idea. So let us look at the layers in more detail. So layer L equal to 1 has the node S with weight with edge of weight to V1I2. So we are drawing an edge from first layer to second layer. With weight x1I. And this you do for all I. Sorry? Oh, so this is just the first layer. So this is basically the S vertex. That's the first layer going to the second layer. And we are just describing how the edges will be from S to neighboring vertices. So neighboring vertices are n minus 1, and when you are looking at a path that takes this x1I, it is like you are building a claw with head 1 and moving to vertex I. x1I is, I mean, you should think of it as the symbolic variable in the n cross n matrix, but you can also think of it as the weight of the 1I edge in the graph. If you are given something in the input, then you should think of x1I as that. And okay, so now let us look at a general layer L. So for L 2 to n minus 1, so intermediate layers, and for all I less than j, in fact let me suppress this. So we are at layer L, and IJL is the vertex. So this has an edge IKL of weight equal to, so the weight should be if you are at VIJL and you want to move to VIKL plus 1, what is the weight that you should put on this edge in the ABP? XJK, right? So that's the thing. Do this for all I less than j 1 to n, and k should be, the only condition is it should be more than I. Okay, so do it for all these keys that are bigger than I and between 1 to n, and for all these ij's also. So this describes the edges that will cross layer L to go to layer L plus 1. So that describes all the intermediate layers and the first layer. Okay, so what is the meaning of interpretation of this? So this grows the I headed claw from J to K. Okay, this is what this what we are doing when we pick xjk in a path in the ABP. In the graph, what we are doing is we are actually walking in a close.
L plus 1.
Where?
Last. For L, Vij, L has an H2V Ik.
Right, yes, that is true. That is what we have in the picture. Yeah, so we are in a claw whose head is I, and then currently we are at J. We don't know what happened between I and J. We also don't care. We'll just want to move to something bigger than I, which is in this case K. Okay, so it's an oblivious, nearly oblivious walk. It's oblivious to what happened before. Okay, and yeah, but we cannot just continue walking. At some point, we have to fold back to I, to the head, right? So that is that needs special treatment, because till now we haven't introduced any sign. So how do you introduce the sign? So that we'll do when we are folding back to I. So that is here. So for L, Vijl, so let me ignore the brackets and the comma. So Vijl has an edge to Vkil plus 1. Yeah, so now I has gone, so if you look at the subscript, I has gone to the second coordinate. So what this is meant to signify is that I headed claw, we were at J, we go back to I, and then we create a new head called K. Okay, so this is the transition point from current claw to the next claw. So this is the place where we should introduce a minus sign. Every claw development introduces a minus sign. So for okay, first talk about the weight. Yes. No, so okay, let me write it down here. Sine of a close sequence is equal to -1 to the n plus r, where r is the number of claws. So let us ignore the -1 to the n, because n is common across all the claws. The thing that is different is this r. How many claws are there in your claw sequence? So whenever you are developing a new claw, just introduce a minus sign. So that is the formula we are using. -1 to the n we will assume to be just 1. So we just ignore that. Okay, so well, or we could have put that in the beginning when we looked at L equal to 1. We could have put it here. It's not very important. Okay, so yeah, here we are jumping to the next claw. So what should be the conditions? Has an edge to Vkil plus 1 with weight minus xji. So usually it would have been just this j to I edge weight, but here we are also introducing a sign. And just introduce this for all I less than j 1 to n and k greater than I. Right, you want the next head to be bigger than I. So that's all you have to remember. So what happened is claw ends, sign changes, and the new head is K. right? This is the interpretation in the walk in the graph. So this describes everything from layer 1 to layer n minus 1. The last layer, what do you do? So Vijn has an edge to T of weight equal to, well, so in the last, the layer just before T, so that has to close the current walk, right? It cannot leave it open and it cannot create a new flow. So if I comma j was the, so you are in Vij, so then you should go to, from j you should just go back to I. Okay, there is no option, and you have to flip the sign then. So this will be minus x ji, and do this for all I less than j. Right. So what happened here is flow ends, sign changes, and flow sequence ends. So not just the flow but also the flow sequence ends here. Is that clear? Do you get the feeling that every path from S to T will give you a flow sequence with the correct signed weight if you take the product of the edge weights? So then ABP by definition computes sum over all the paths, which will be determinant. So those are then the observations. So the observations are each ABP path corresponds by design to a unique closed sequence of G. Moreover, the signed weight, the respective signed weight matches. So every part defines a unique closed sequence, and when you look at the sign weights of these two, they are the same. And second observation is that each closed sequence, okay, so when you look at a path S to T in this ABP, you will get a closed sequence, but you also have to show the converse, that every closed sequence in the graph has been implemented as a path. Is that true?
I believe because you have all the available transitions, like you can go wherever you want to. Because
right.
all the vertices that they are identical.
Yes, but we fix the first head to be 1. Is that kosher? Could the head have been 2?
You can. No, I mean you have a closed sequence to. We can add an edge. Or we can add a V11.
No. So note that the closed sequence has length exactly n. So I think the heads are already fixed. So the first flow.
You could start with 2 and manage.
You could start with 2 and okay, I see.
The sequence of it matter, right? Yeah. No, but one has to be covered by something, right? If one is anywhere, then that will be the head.
Yeah, so basically these closed sequences that start with 2 are not being produced here. But will it matter? It won't matter because it doesn't contribute to determinant.
You're building the ABP for the determinant.
Correct. So that is that's the only small point, that we don't really care about all the closed sequences. We just want those closed sequences that have a potential of contributing to determinant. So those are being produced. So each closed sequence of G of with first head equal to 1 corresponds to a unique path in G. Is that clear? So the only thing we have fixed here is the first head. After that, you have all the freedom. You can move wherever you want to, but that is fine. Okay, so these the sum of over all the paths of the sign weights will give you determinant. So that finishes the proof. Right, so
I mean, when you look at any monomial of the determinant, you can just start off with sum x 1 comma I, right? So I mean, this is why I guess this is fine.
Right,
So,
right.
but you have to, I mean, making an argument like that, you have to make sure that everything cancels, right?
Yes, but we showed everything cancels last time, right? Because if there's anything that you don't cover, then that is bound to get cancelled. If you don't cover any particular vertex, if there's a repetition, then that is bound to get cancelled.
So for that you have to observe that a closed sequence that starts with head 2, head equal to 2, under join or break will give a closed sequence of head equal to first head equal to 2. So in the partition we are actually removing elements together with their transformation. So on the subset also our map is actually a involution. Yeah, so those are minor points. This basically is done. So what did we learn from this? So this is actually a big result. It shows that determinant as a polynomial has an iterated matrix multiplication expression where the matrices are n square cross n square and there are n of them. Okay, so determinant can be kind of factored into matrices. So it was a determinant of an n cross n matrix, but these factor matrices that you are multiplying, they are slightly bigger. They are n square cross n square. So that may be something to optimize, but we don't know whether it can be optimized. It's an open question. This is the best representation for determinant. And then second thing, once you convert this IMM into circuit, so since you have n matrices to multiply, right, you can do it by recursively by halving, and so that gives you a circuit. And what is the depth? Same as the number of recursive calls, right, which will be log n. So you actually get a log n depth arithmetic circuit that will compute the same thing, and its size will obviously be polynomial. So that gives you a very fastest possible parallel algorithm. So determinant, and there is no division happening. So over any commutative ring has log n depth poly n size. If you analyze, the size is also not too bad. It will be, I don't think it will be more than n to the 5. So you have n square cross n square matrix and you have n of them. So n to the 5 I think is a trivial bound on the size. it's not too big a circuit, but the time that it gives you is log n. Right, so this is an improvement even over the first result you saw, where we showed determinant is in Vp. There we got log square n depth. Now this is log n depth. Slight difference is that here this is unbounded fan in, fan out. Unbounded as in it is not bounded by a constant, it is not 2. So fan in and fan out are bounded only by the size, because when you look at the recursive implementation of iterated matrix multiplication, so when you want depth to be log n, then you actually are forced to add and multiply many things. So addition multiplication gates are actually multiplying many things. Okay. Yeah, maybe multiplication you can bound the fan in, but addition certainly is unbounded. You have to add many things. So yeah, so we finished this. Any questions? Yes.
Is there something similar known for permanent?
What do you mean?
I mean, do you have anything to compute permanent, like a result like this? Permanent has a
polytime algorithm.
You don't have an AVP like that. I mean, what is the barrier? That is what I'm asking. Like, when you try to implement this.
Oh, the barrier is that how do you show that sigma over close sequences? Right, the cancellation. In the proof, we had this involution, which was cancelling things. So that was happening because of the sign. So that kind of a result we don't have for permanent. We don't have a mathematical result for permanent.
So if we ignore the signs, then possibly we might overcount or do more.
No, so then you would just, yeah, the more close sequences you look at, more things will get added. Yeah, it never converges to something meaningful.
So this was unbounded fan, and like it shouldn't be a problem like if we consider as it bounded as well, because if we like bound the fan in, then it should not blow the like depth would increase. But
depth will increase, yeah. So then you will get the previous result. Depth will become log square n. Yeah, because if you have if there are n to the 5 things going inside an addition gate, again by divide and conquer, you can implement this in log n depth, log of n to the 5 depth. So then the depth just gets multiplied by log of n to the 5, which is order log square n. So then you go back to the previous result, but the previous result does not give this result. So this is really a stronger result, and except the constants in the exponent of size, this is really optimal. You cannot improve this. Neither in theory nor in practice. So yeah, but there is a meaningful question for determinant that it has not answered, which is the assumption of commutativity. So what can you say about determinant over non-commutative rings? So for all practical purposes, this result is good because, well, you only look at determinant usually over fields or integral domains. So those are all covered. But if one day you choose to pick your entries in the matrix as being matrices themselves, so you are looking at determinant of a matrix whose entries are matrices. So then actually you are looking at determinant over a non-commutative ring, because matrix algebra is non-commutative. So we don't know results for that, except just brute force computation.
There, it would even be that the determinant of the matrix is equal to the determinant of the matrix transpose, right?
Right. Yeah. So it will really depend on the order, the way you are multiplying these entries. Yeah. So that is a question which is not answered or even considered here in this analysis. So this was. So I think currently it is known that for general non-commutative rings, determinant is as hard as the usual permanent. So there is, I think, no hope for doing this efficiently. But you can still ask for special rings. So I don't know what are the results there. Any questions? Right. So this completes the discussion about basic models and what can they compute, right? So this shows that determinant and ABP are the same, and ABPs are contained in circuits. ABPs are, I mean, circuits are at least as strong as ABP, believed to be stronger. And where do you think are formulas? On the left, yes, but that we have not shown. So sometime we will show that formulas are on the left. So formulas are weaker than ABP, which is equal to determinant, and these are weaker than circuits. Circuits also, we have two kinds: circuits with bounded with Pauli degree, so that is VP, and we also can look at circuits with unbounded degree. I mean, general degree. Okay, so the circuits with Pauli degree is VP. That's the VP class. And circuits with no assumption on the degree, just on size, this is the class VP subscript NB, which just stands for not bounded degree. Yeah, so this is currently the summary of what we have learnt in terms of complexity classes. So formulas you can call as defining complexity class VF. Okay, let's say Valiant's formula. ABP you can use it to define a complexity class called VBP. So Valiant's branching programs. So these are basically polynomial families for which there is a polynomial families with indexed by the number of variables n, for which there are ABPs of size poly n. Right. So these are classes of polynomial families: VF, VBP, VP, and VPNB. Right. So we have some understanding of how they compare and how powerful they are, but we don't know anything else here. So we don't know whether VF is strictly weaker than VBP, VBP is strictly weaker than VP. Well, we know that VP is strictly weaker than VPNB, just because of degree, right? So that we already know by definition. But this is an open question, and strictness of these two, the first two inequalities, it's an open question. So what we will do now is we will look at some very powerful results, structural results here. Okay, so circuits with Pauli degree, which is VP. So we'll now prove some structural theorems about VP. Okay, which will really be some of them will be very unexpected. Okay, you will not conjecture them looking at the definition, just like you will not conjecture determinant equal to VBP from the definition. So equally unexpected results. So oh, and in the previous thing, there is another branch which is by adding non-determinism. So that gives you VNP. Right, which obviously is our central open question. So these are your complexity classes in this course. You can define more, but those will be straightforward definitions. Okay. So one thing about arithmetic circuits that we'll see over the next few weeks or months is that they have some striking self-reducibility. So they have striking self-reducibilities that makes studying very special cases worthwhile. So the term self-reducibility means that general arithmetic circuits, you can convert them into something much simpler, a much simpler arithmetic circuit, a special case of arithmetic circuits. And so then studying these special cases becomes an interesting question. So if you can understand these special cases good enough, then you actually will have results about the general circuit model. Okay, so these self-reducibilities are actually very special to the algebraic model. Their Boolean analogs don't exist. Okay, so if you try to do the same thing for Turing machines or Boolean circuits, those things are false. So this will really be a consequence of algebra. So the first special property that we want to show is, well, so a circuit computes a polynomial, let's say n variate degree d. So you can talk about degree d homogeneous part. So homogeneous parts means that you only want those monomials and respective coefficients where the degree is the same, let's say d. So you want to extract those monomials whose degree is d. There may be monomials of degree d minus 1, d minus 2, you want to drop them. So the question is, if the original circuit has a small size or the original polynomial has small circuit complexity, what can you say about the homogeneous part? Is this also easy to compute? Right, so this is called homogenization. So a polynomial f is homogeneous if all its monomials, well, when I say all its monomials, I mean those that are in the support. I don't care for those monomials whose coefficient is 0. So monomials that appear in F with coefficient non-zero, they have the same degree. Okay, so F has equidegree monomials, so then we call it homogeneous, and a circuit is homogeneous if, so how do you want to define this homogeneous circuit?
At every gate, I probably want to.
Right, so the definition will be syntactic, so it should hold for every gate, not at the root, but every gate should be computing homogeneous polynomials. If every gate computes a homogeneous the theorem that we will show is I'll call it homogenization property of circuits, shown by Strassen. So say F has a sizes circuit. So then for all i's where D you can think of as the degree of F. So for any I you can compute the homogeneous part of F using a homogeneous circuit. So there is a homogeneous circuit Ci of size Sd square that computes degree I homogeneous part of F. So for every homogeneous part there is a homogeneous circuit of size slightly bigger, S times D square. And in fact the result is slightly stronger, so I don't need to assume D to be the degree of F. D is just any number. So basically the circuit may have a very large degree, but if you are interested only in low degree parts, they can be computed efficiently. Okay, so the thing becomes expensive only when you start asking for very high degree homogeneous parts. Anything that is low, that can be extracted out in size Sd square, which is small. How do you show this? It has a simple proof. Right. So since you want a homogeneous circuit, already this demands that from the very beginning, so from the leaves, you should be computing the homogeneous parts separately. Okay, so at any point, any layer, you can assume that you have currently the homogeneous parts available of an intermediate polynomial, And so when you want to add two such things, you do it homogeneous parts, I mean you add the corresponding homogeneous parts to get another homogeneous parts for the sum, and when you want to multiply, then yeah, so then using the definition of polynomial multiplication, you can again do this in a homogeneous way to get the homogeneous parts directly. Sorry?
The product does not do anything.
No, I mean, if you have x1, x2 and x1, it's coming up. If you just multiply it, then this is homogeneous of.
No, so it's a, so you have two polynomials g1 and g2. Let's say in the original circuit you had two polynomials g1 and g2 which were non-homogeneous. So the multiplication gate that is multiplying these two, this you have to implement by a homogeneous circuit. So you actually have to break g1, g2 into homogeneous parts, and part by part you have to multiply and output those things by different multiplication and addition gates. Yeah, so this is what the simple proof idea is, and you implement it just by formally by induction. So without loss of generality, assume C has fan-in just 2. If it had more fan-in, you can just no, okay. If it has more fan-in, then a similar proof will work. Okay, the proof will not really change much. No, in the multiplication it may change. Actually, assume that it has fan-in 2, and if the fan-in is more, then convert it into fan-in 2. So this will increase the size slightly, but not by much. So we will be using this fact. So for any gate G in the circuit, we intend to construct G0, G1, GD such that GI computes degree I part of G. Well, okay, so I want to give a more general proof, right? So I have to say, okay, let me say that this was strictly less than D. I want things from 0 to D minus 1, and what I will do here is up to D minus 1, it is correct. So G0 to GD minus 1 are indeed the degree I homogeneous parts. GD is the rest. So degree greater than equal to D part of G. Okay. So 0, 1, dot dot D minus 1, these homogeneous parts plus the rest, which is then the parts of degree D or more. So this is what we want to maintain. So we are actually building from the leaves inductively, we are building another circuit C prime such that for every gate G in C, there will be an analogous computation happening inside C prime in a completely homogeneous way. Okay, so think of another C prime being built inductively. That is our goal. That is our strategy. We shall construct GI recursively or inductively. So let G have children U and V. Right, so G has fan in is 2, so U and V are the only two gates which are feeding into G. Now G itself may be an addition gate or multiplication gate, so we have to handle it separately. So case 1 is easy case, which is the sum. G is U plus G is an addition gate. Well, so for U, you have U0 to UD available. For V, you have V0 to VD available. You just do the obvious thing. So define GI to be UI plus VI for all I. Right, so this is fine. This is the property of this is that it's a homogeneous addition. So using homogeneous addition gates, you can compute GIs now inductively. And how much has the size grown? Not much, by order D, just an additive growth. So this is under control. So next is when you are multiplying, this will grow slightly more, because here what will be GI? Right, so this was actually this. These are available to you, UIs and VIs. So now when you want to compute the ith homogeneous part, what do? Well, you correct. So U0 should be multiplied with some UI. Oh, sorry, VI. And U1 with the one behind VI. And U2 with the one behind, and so on.
Then I think we can handle quite a bit of Fanon, right? Because this is just x plus y equal to d. They will have three variables: x plus y plus z equal to d, something like that. So we just want to keep that the sum of the degrees is I or d.
No, but
we take something from here, we take something from here. What we can take from there is fixed.
but they are not just UV. There is U, V, W.
Yeah. So once you take something from U and something from V, what you take from W is fixed.
No, but the number of products exponentially starts blowing up. If you are multiplying R things, then you have d to the R many products. So we don't want that actually. We don't want to go there. Let us just do with the Fanon 2. So define GI as now this convolution Uj times Vi minus j. J is 0 to I. And do this for all I. This product is homogeneous. Homogeneous multiplication gate. And also the sum is homogeneous. Okay, so we have computed all the GIs. The price we pay is, for every GI we have around so order D, many multiplication gates that we have introduced, and so there are order D square many gates being introduced. Yeah, so as you can see, the multiplication Fanon is not growing. This remains 2 in the end, but the addition Fanon is D. Okay. Yeah, actually one has to be careful here also. In the boundary case, this should only go up. You should only go up to d minus 1. Yeah. Because if you start introducing the dth parts, yeah, there it's inhomogeneous. So, but then you can define it easily. So GD is just U0 VD plus U1 yeah, so D minus 1 can also contribute now. And goes up to UD. So everything. So the properties of homogeneity are there only for these G0 up to GD minus 1. GD we can compute, but we don't care about homogeneity. Yeah, so I should have rephrased it maybe in a different way. So GD part is really not homogeneous. Will that be a problem? Well, okay, so it is still fair to say that the resulting circuit is homogeneous circuit, because if you are only interested in parts up to d minus 1, then at no point of time in your intermediate computation will you need degree d or more homogeneous part. So actually GD could be forgotten. If in the end you don't want to compute, you only want to compute up to d minus 1 homogeneous part, then at every intermediate computation GD could be forgotten. Okay, so this part is actually not needed. This can be dropped. If you include GD, I mean GD also can be computed, but if you include, then there is this slight non-homogeneity that is being introduced. Okay. So note that on introducing these extra gates, for each gate in C, we get a circuit C prime whose size grows per gate by d square, so its size is now SD square. Is that clear? Yeah, so we are computing all the homogeneous parts up to d minus 1 using a homogeneous circuit. Okay, so that was not too difficult. So what do you do with the formula? So you are given a formula, which means fan out is 1, and you are interested in computing all the homogeneous parts as formulas. So fan out should remain 1. So you observe that here in our proof, we are using this uj. We are assuming that uj has been computed once here below, well, here uj and vj have been computed, and then we are using them again and again. So the fan-in of uj is more than 1. So that is not allowed in the case of formula. So this proof will fail. Does it mean that you cannot homogenize a formula? Yes or no? Yes. No. So Abhibhav doesn't believe.
Maybe.
Yeah, so maybe is the correct answer. So it can be done. Think about that. It's a proof even simpler than what we did. Okay, so no, but that I should clarify. If your demand is to get a homogeneous formula, then that I think is an open question. But if you just want a formula for the homogeneous part, formula complexity of homogeneous part, that you can show is low. But if you also want the resulting formula to be homogeneous, then I think it is not clear. Yeah, so this is a fair question. Do this for formula. Do some things but not everything. Any questions? Okay, so we move to the next property, which is partial derivatives. Okay, so since we are working with polynomials, after you have understood the homogeneous parts, you want to now we will want to understand other operations on polynomials. So the first natural operation is differentiation, right? So you differentiate, let's say with respect to variable x1. So what is the complexity of the derivative polynomial? And you can differentiate now, you can look at higher order derivatives. So like x1 square or x1 x2 or x1 x2 x3. So what is the complexity of these partial derivatives? So let do xi be the partial derivative operator with respect to xi. So these are the first order derivatives, the simplest ones. So we know that do xi, it takes n-variate polynomials and send them to itself, the same ring. And this is a linear operator. Why is it linear? Simply because f plus g derivative is equal to derivative of f plus derivative of g, that's all. Yes.
I mean, it's also f everything except xi linear, right?
Okay, fine. Sure. Yeah.
Sorry, what?
Well, he is saying that if you take the base field to be the function field having variables x2, so say I is 1, so do x1 has the property that if you look at the function field with variables x2 dot dot xn, so over this function field you are looking at univariates in x1. So do x1 is actually also f x2 dot dot xn linear. So you can also push the other variables inside. In that function field also it is actually a linear operator, but it has the same proof. Moreover, it has this really unique property that well, so it preserves essentially the addition operation, but it doesn't preserve the multiplication operation. There it has a unique, it follows a unique identity which is called the Leibniz rule or the product rule. It also has product or what is called Leibniz rule, which is dou xi fg is f times, so differentiate g or differentiate f. Right, this is one nice property of derivatives. Right, and goes without saying that the third property is if you differentiate a polynomial which depends on, okay, if f is free of xi. So this also we will be using all the time. Derivative vanishes unless it depends, polynomial depends on xi. So yeah, what we'll do next time is show that these first order derivatives, they can all be computed simultaneously by a circuit whose size is the same size and the same depth as before, okay, which should be a pretty surprising thing because there are n derivatives, first order derivatives, all of them can be computed in essentially the same size and depth, okay. So that is not at all clear from the definition of a circuit. Any questions? Okay.